My name is Thomas Pierce. I am a senior mechanical engineering student at VCU. I am the project manager, and my background is in construction. I did that for about 6 years before coming to VCU for my degree. To give some context to the project, it's part of ongoing professor-led research at VCU, part of a lab that is developing new methods and techniques for using magnetic material. So we're working with our faculty advisor, Dr. Barua, to give her the resources for her and future graduate and future undergraduate students to be able to print components that have unique magnetic properties that currently can't be produced through other methods. We hope that by the end of the semester, we'll have the ability to create filament with specific and measurable particle alignment, and that ability will allow the lab to innovate new technologies in communication, manufacturing, and defense applications.
Hi, I'm Micaiah Akyeampong, an undergraduate senior in mechanical engineering at Virginia Commonwealth University. I am a member of the Fabrication of Magnetic Filaments with Fused Deposition Modeling Technology capstone project. For my role is the finance manager. My responsibilities include managing our project budget, overseeing the procurement process, and meticulously documenting all parts and materials. I work closely with the manufacturing engineer to ensure that all information is accurately organized and any gaps in sourcing materials is promptly addressed. Our team is focused on cost effectiveness and efficiency for this project by extensively utilizing 3D printing for component fabrication, and mainly using off-the-shelf parts from common suppliers such as McMaster.
My name is Vincent Mazzochette. I am an undergraduate mechanical engineering major here at VCU. I am a retired veteran of the United States Army after 20 years of service in the aviation field, now seeking to further myself by completing my bachelor's and possibly continuing on to a master's degree. I am serving as this capstone team as the design, system, and manufacturing engineer. We are working to develop an extruder to make 3D printer filament that has embedded material of our choosing. Those will range from thermally conductive materials to magnetically permeable or impermeable materials. I will walk you through the extruder in its current form. Everything is situated on an aluminum extrusion frame that allows us to adjust the position of each of the components, as well as keeping the system portable. Starting at this end, we have the control box that houses the power supply, Arduino microcontroller, ramps, motor controller, switches, relays, and other necessary control items, as well as provides a handy place to mount our control screen. The pressure in the system comes from a NEMA 23 motor with a gear reduction that is coupled to an auger-style drill bit that is turned in the reverse of its normal direction. This has the effect of moving the pellets of the raw material and the additives into and down the barrel through the heated zone and out of the nozzle in a molten state. The heating is provided by a 110 volt heater controlled by a PID loop and a solid state relay by the Arduino in the control box, which has to be tuned to maintain a consistent melting temperature during the extrusion. After the filament leaves the nozzle of the extruder, it passes over a cooling fan that starts the cooling process. However, it stays partly molten at this phase. It then passes through a filament diameter sensor. This diameter sensor uses an LED which shines down onto a light sensor. As the filament passes between these, the width of the shadow produced is translated into a voltage that is fed back into the Arduino microcontroller that allows for the control of the filament diameter. This is the diameter sensor. The next component is the puller. The filament passes through two soft rollers, which are driven by a NEMA 17 motor with another gear reduction to allow for fine RPM control. The Arduino reads the diameter of the filament at the sensor and compares that against the pre-programmed expected value that we have set, and again, using a tuned PID loop, either increases or decreases the speed of the puller. By increasing the puller speed, the filament is stretched more, thereby reducing the cross-section further, and of course this means reducing the diameter. Conversely, by slowing down the puller motor, the filament is stretched less and the opposite happens, and the diameter of the filament produced after that can be increased. Lastly, the filament coming out of the puller is fed into the winding mechanism. This is powered by a DC gear motor that drives the outer edge of a mounted filament spool. This in turn drives a set of gears down to a worm gear and a rack which oscillates a filament guide that moves back and forth to distribute the filament onto the spool evenly so that it can later be dispensed while printing without tangling. Due to the fact that different diameter spools can be mounted to the winder, the DC motor must also be speed controlled along with the puller motor, but with a scaling factor ratio that can be set to adjust for different diameter spools.
I'm Kamau Bey, mechanical engineering senior, and currently serving my 6th year as an aviation operations sergeant in the United States Army after a couple years of active service. I'm a member of the MNE 24503 Capstone Project, otherwise known as the Fabrication of Magnetic Filaments for Fused Deposition Modeling Technology. I operate as the testing and logistics engineer on the team. As the logistics engineer, I work to align stakeholder priorities within the framework of the team's design objectives. This is done by keeping meeting minutes or maintaining open communication with our faculty advisor. As the testing engineer, I facilitate the team's goals, data tracking information provided during testing cycles. I work with the manufacturing engineer, Vincent, to test our extruder's capabilities and refine control processes. Half of this responsibility is organizing information through testing worksheets created by myself that's used to log down time-stamped occurrences, causes of those occurrences, and remediation efforts made during the testing cycles. This is a live document that's continuously updated on our document management platform, Edusource. The other half of this responsibility is leveraging the information used in testing cycles to implement improvements on the extruder functionality. So one of the additional duties of this role is tracking progress and keeping organization of the test samples that we produce. So I have some samples here. So when we began extruding filament, we started extruding ABS filament. And we started using clear ABS feedstock fed through the extruder and producing some pretty brittle but clear brittle filament. And then we started implementing some black colorants. This was all before we got a diameter sensor to actually read the diameter of the filament. So a lot of this is non-uniform and it was pretty straight through testing. And then once we were finished with ABS filaments, which was not a long process, we eventually switched over to PLA. So we had some clear PLA filament here. So we started using raw PLA version pellets, feeding it through our system. And while we were purging our ABS, might not be able to see this, but there's some black spots where there was some ABS remaining within the system. We began to get clear PLA, pure PLA for the most part. This material was still pretty brittle. It was not very malleable, pretty hard to spool with varying melting temperatures sometimes. And then we began to start testing with color. So we started with a blue colorant that we received, and this was around the time when we got our diameter sensor. And so our diameter sensor was able to pick up our diameter with color. So we originally went with a non-measured mix by weight of color with PLA. So we had clear PLA and then we had colored PLA pellets that we'd mix. And so this was an unmeasured test to test the capabilities of the diameter sensor or to just test the functionality of the extruder. And so there, it was shown that there's some sort of plasticizer or something that's able to allow this filament to be usable, at least in terms of how flexible or durable it is without being too brittle as compared to the clear PLA. So we were noticing a little bit better results with the colorant that we were using. And then we began to record more of the diameter sizes. And then we started to play around with the colorant mixing percentages, where we went from 5% mix all the way down to 2% mix in some instances, to see how well the diameter sensor would read, or how uniform our filament would come out when there's more blue colorant added versus less blue colorant added. We found that a stronger mix of blue colorant was more successful in extruding, and we went from 5 all the way down to 2, and we found that between the 3 and the 2% mix by weight range was where we were running into a lot of misreadings in the diameter sensor, or not uniform diameter. Our diameter target is around 1.75 millimeters with 5% tolerance on either side. So that was what we were trying to achieve in our extruding testing. And then we began to settle on 4% mix by weight, so 4 grams of blue colored filament or pellets to 100 grams of clear raw PLA. And with 4% mix, we were able to get a lot smoother color saturation throughout our spool. We were also able to get concrete and consistent readings for our diameter, sensor, and we were able to get a lot better pliability and flexibility within our filament. With the 4% filament mix, some of the filaments have been experimented with spools of filament that are within the acceptable diameter tolerances of about plus or minus 5%. This is used to test the integrity and printability of the produced filament by our extruder. And one way to test that was to run our filament through an extruder. And by doing that, we were able to assess some of the printability or feasibility of our filament. One way to do that was to print benchies, which are typical products that measure the printability of our design or of our filament, and especially the performance in printing unique or complex designs. So we began by printing a benchy, or like a little boat, about 50% of the original size that you would normally print. And then we upgraded that to a 75% to scale test print of a benchy. And those are just ways that we are able to assess how printable our filament is, whether it jams, and whether the printer accepts our uniform diameter or not, and while we were printing with a Creality Ender printer, 3D printer. Moving forward, we would look to continue testing with a new batch of red pellets this semester, mixed with clear PLA feedstock. We anticipate refining more process controls for the extrusion process and increasing the efficiency of the extruder by extending the barrel and implementing multiple heating stages to encourage better material mixing while in a molten state. This is all done to increase the efficacy of the extruder itself, and later in the semester we will begin our Halbach array design installation on the extruder to accomplish some metallic composite feedstock for magnetic particle alignment during the extrusion process. This will begin a new phase of testing where PLA virgin material will be mixed with barium hexaferrite, which will in tandem assess the abrasion resistance and durability of our extruder. Thank you.